computer. We're going to continue that theme of selectivity with our second half here, and we're going to look at other ways of getting to reduce the system such that we have the exact amine we want, whether it's primary, secondary, or tertiary. So the next way we're going to talk about this is we're going to talk about the reduction of amides, okay? Now, when we did amides in our carboxylic acid chapter, we found out we could use a ammonia and get a primary amide, and it stops there. Unless you use extraordinary measures, you only get one acylation of that nitrogen. So if you had a primary amine and you acylated, you would end up with a secondary amide. And if you had a secondary amine and you acylated it, you would end up with a tertiary amide, 3 different carbons onto the nitrogen. So we were able to do just adding one group, no matter how nucleophilic that amine was, we always added one acyl group to it. And so that gave us a really good stopping place for our system. Now we're going to continue on with that, and we're going to reduce down that carbonyl compound to give us a CH2, to give us our amines. Okay, so only in the amide system does it matter where you can get a primary, secondary, or tertiary amine based on what you're going to do here. So in the case of our primary amine, with reduction with the lithium aluminum hydride gets your primary amine. Notice in this case, you have the exact same number of carbons you had in your carboxylic acid. Okay, we didn't lose it like in the Curtis or the Hofmann rearrangement where we had carboxylic acid but lost that carbonyl. In this case, we're looking more like as if we attacked it with an alkyl halide because we have the same number of carbons we had in our carboxylic acid. Okay, and if we already had an R group on that nitrogen here, only the carbonyl is reduced, leaving the other group untouched. So by having an alkyl group on our amine and then reducing our acyl group down, we'll get to our secondary amine. And if we had a secondary amine that we acylated to get our tertiary amide, we'll end up with our tertiary amine. So primary amide gives us primary amine, secondary amide gives us secondary amine, tertiary amide gives us tertiary amine. Okay, all with the same reducing agent. Again, just reducing that carbonyl down to a CH2. Okay, so now that we know how we can make them selectively, we can selectively make primaries by several different methods by adding or reducing the number of carbons in our chain or maintaining the number of carbons in our chain. Now let's talk about how we can use them as bases. Okay, so they react as Bronsted-Lowry bases, but they also react as Lewis bases. So in the case of a Bronsted-Lowry base, we are going to use that lone pair to reach out and grab a hydrogen and create our conjugate acid, which is our ammonium salt. Okay, so we can do this with or without on our group here. As long as you have a lone pair there, it will react as a base and will form your conjugate acid in some form of equilibrium. Okay, remember that the aliphatics are more basic, and therefore our pKa's of our conjugate acids are the highest in the set, would be the aliphatic ones, and it decreases as you go down from away from the aliphatics to the aromatics and into the conjugated aromatic systems. Okay. So because of this, we can use these as bases for both strong acids to generate our strong ammonium salts, and with our counterbalancing new conjugate base here. Or we can even use them with things like the carboxylic acids, which are not as strong. However, the pKa of that protonated amine is still higher than that of our system. So that means the equilibrium lies in the direction of the amine salt of our carboxylic acid. Okay, so that is a strong enough base to deprotonate our carboxylic acids, and we anticipated it to react with a very strong acid as well. Okay, so let's talk about reacting that with a compound called nitrous acid. Okay, so the first step we would think of when we are reacting this is it would form that acid-base reaction. But what it actually does is it undergoes a different reaction for us. Okay, so nitrous acid is N hydrogen, nitrogen, oxygen 2. Nitric acid is the hydrogen, nitrogen, oxygen 3. Okay, so this is not a very stable acid. It likes to decompose and form other things. But we can then react it, make it in situ by using the salt of the nitrate, nitrous. So this is sodium nitrite. And so it reacts with that to form nitrous acid in situ and forms a little bit of the sodium chloride, one equivalent of sodium chloride out of that, okay? So now what this does is this does a reaction with amines. It can technically work with aliphatic amines, however, these things tend to decompose very rapidly, but it's used extensively in aromatic amines. So if you start with aniline and treat aniline with HCl and sodium nitrate, you actually generate a new compound called a diazonium salt, okay? This diazonium salt, right here, this diazonium salt means that it is a good leaving group. It can leave as a neutral species if you attack your benzene with a nucleophile, okay? Remember, when we did all those reactions in the benzene chapter, we actually attacked the benzene with electrophiles, okay? The benzene was electron rich and was attacking electrophiles. Here we've generated something that makes it a very good leaving group. It's going to leave as a neutral gas, nitrogen, and therefore you can displace this diazonium salt with a variety of negatively charged nucleophiles. So this is completely backwards from what we learned in the benzene chapter, but it fits really well in here because we can now make substitutions on these benzene rings we couldn't do before. We can add hydroxy groups and alcohols and other things to the system, okay? So this is really a different reaction. We're looking at now a nucleophilic aromatic substitution, and it works predominantly only with these diazonium salts, okay? So let's talk about that reaction a little bit more. It gives us a new thing that we can do with benzene, but it always starts with your aromatic amine or your aniline, okay? So you can take your aromatic amine aniline and react it with our nitrous acid, and it'll generate at very low temperatures our diazonium salt, okay? Our diazonium salt here has a great leaving group, nitrogen, and then we can attack it with a wide variety of nucleophiles to generate a certain number of different products. Now, in the case of using copper and copper-based salts, we end up doing what's called the Sandmeyer reaction, where we can use the copper to support our nucleophile and generate out the back end our new aromatic nucleophile bond and nitrogen, okay? So in the case of copper chloride, copper bromide, or copper cyanide, we get a direct attachment of the chlorine, bromine, or cyano to the location on the aromatic region where the amine was, where that NH2 was, okay? It doesn't move around the ring, it doesn't go ortho-para-meta, it goes exactly substituting at that position. So if you already have an amine on your aromatic ring, you know you can get exact displacement at that site by going ahead and creating your diazonium salt, using your nitrous acid here, and then by adding a copper salt of copper chloride, copper bromide, or cyanide. You can also add hydroxide at that position by using copper oxide and water at the end. Okay, so again, you're getting exact substitution. Okay. Now, if you remember, when we were looking at those aromatic ring reactions, we did a lot of things where we chlorinated with iron chloride or we brominated with iron bromide, but we didn't make the iodine or the fluorine. The iodine was not reactive enough and the fluorine was too reactive. This gives us an opportunity to be attacked by a nucleophile to displace the diazonium salt. And that allows us to get to our aromatic iodines and aromatic fluoride reactions. Okay, we just have to use slightly different reagents than the chlorine, the bromine, or the cyanide. Okay, and the last of the set we can do here is just like when we wanted to do other removal of oxygens or removal of other systems, we can actually add an acid to it using a strong Lewis acid, in this case, a phosphoric acid. We can actually take that amine off. So this, because we can take that amine off and put a hydrogen in its place, we need to start thinking about, oh, we can use that amine as a protecting group to protect a location and then regenerate our hydrogen at the end of a multi-step synthesis. So that's one of the benefits of these diazonium salts. We can put a lot of different groups there exactly where we want them. So let's go into that a little more detail on the next slide here. So the Sandmeyer reaction specifically is those copper salts putting the chloride, the bromide, and the nitrile on the benzene ring. And again, it puts it on specifically at the place the nitrogen was, not where an ortho, meta, or para director might direct those materials to be. So let's look at the case of the toluidine, which is the toluene with an aromatic amine on it. If we treat that with the sodium nitrite and acid at a low temperature, it'll generate our diazonium salt. These are very reactive, very easy to displace. When we add our copper chloride to it, we have the overall reaction generates our chloride directly where the nitrogen was. Remember, if you just tried to chlorinate this system, it would actually chlorinate ortho, meta, para to the other systems, to these directors. It would go in these other locations right here. So we're getting substitution at exactly the place where the amine was. And we can do that same thing with bromine right here. In this case, we have the metachloro. We want to get the metabromochlorobenzene here. If we just brominated this chlorobenzene, we would get it in the para position or occasionally in the ortho positions. If we want it specifically in that meta position, we can take our nitro compound, chlorinate, and then reduce down our nitro to give us our amine. Then doing the Sandmeyer reaction with our acid and our nitrite to generate our diazonium salt. Hit it with our copper salt here, and we generate exclusively the meta isomer of this. Again, displacing only where the nitrogen was and extruding out nitrogen gas as our byproduct. So that's a really good byproduct to have because it just is really easy to clean up the reaction at the end. And then again, you can do it again even with electronic drawing groups on the system. And again, it will only react with the amine to generate the diazonium salt. And then you can displace that diazonium salt. So this becomes very synthetically useful, and you can do it in the ortho, para, or meta position. It doesn't matter. You can put it exactly where that nitrogen is and get that substitution you want. Okay, like I said before, you couldn't really easily iodate or fluoridate these benzene rings because the reagents were either non-reactive or too reactive. So using the diazonium salts to get the iodine on the benzene ring and the fluorine on the benzene ring works very well. In the case of iodine, we do exactly what we do before. We create our diazonium salt here, and then just adding a nice potassium iodine. Our iodine's a strong enough nucleophile to displace the diazonium salt and generate our nitrogen plus our substituted iodo product. Okay. And again, this reaction doesn't matter whether there's an electron donating group or an electronic drawing group associated with it. It will still do the nucleophilic aromatic substitution reaction with the nucleophile coming in after you form the diazonium salt. Now, in the case of fluoride, because it's very hard to get the fluoride to be in the correct position and at the correct electronics, we actually do a trick where we use fluoroboric acid to make our salt. So instead of having, like in the case here, we have the sulfate salt or we have the chloro salt if we used HCl, we actually use the fluoroborate, hydrogen fluoroborate, to create the salt. And so when we heat that, that means the fluorine, those nucleophilic fluorines are right near the site we want to react, and we can end up getting substitution with a fluoride right here without fluorinating any other part of the ring, and generate our nitrogen plus BF3 is our spit out here as a Lewis acid. But the key here is the hydrogen fluoroboric acid to pre-generate this salt, and then when we heat that salt, it thermally rearranges to give us our fluorine attached to that nitrogen position. Okay. So we have a couple more reactions we can do there. So you see that these diazonium salts actually are very useful in the fact that we can use a wide variety of other functional groups once we have that nitrogen on the ring. Okay. So the last thing we want to talk about here is the substituting that nitrogen of the amine with an oxygen. Okay. So in this case here, we use a copper salt plus water. The actual OH comes from the water in the system here, but we pre-coordinate with the copper salt to make it work. And of course, it's stepwise like before. We create our diazonium salt here. Doesn't really matter what the counterion is, as long as it's not the fluoroborate. And then we heat it up with copper and water and copper oxide. We'll generate the phenolic derivative from our aniline derivative. Okay. So, and this is where it becomes kind of useful, is you can use that amine as a blocking group or as a directing group to get substitution exactly where you want to go. So let's say, for example, you wanted the metabromo toluene right here. If we just brominated toluene, we'd get the para position and we'd get the ortho positions. Those are the places we get our bromines happening first. If we tribrominated it, it would be in those positions. We would not have any metabromo toluene in that reaction. So what we can do is we can trick it. By directing the bromination, we can get it to be exactly in that place. So let's look at how we do that. We'd start with an amine blocking one of the positions we don't want the bromination to happen. In this case, the para position. Okay, and then we'll react that to form the amide right here. The reason we want to do that is we want to deactivate the ring slightly and make sure that the bromination happens next to the nitrogen. Okay, now remember, our methyl group is only slightly activating. Our amide here is still more activating, and therefore it's going to promote bromination in its ortho position right here, which is meta to the toluene. Then once we do that, we can generate our diazonium salt. And by heating that diazonium salt with phosphoric acid, we're going to remove that diazonium salt, leaving us a hydrogen. When it does that, it leaves us with our primary, our bromine doesn't change position. We add a hydrogen to that para position, and we end up with a high yield of our exact location of our bromine. Okay, so we're using it kind of as a protecting group, but then we can remove it and put a hydrogen there. You could also put an iodine there, you can put a fluorine there, you can put an OH there, if you choose that last reagent in the system after making your diazonium salt. So the diazonium has a lot of different things you can do. Okay, so what else can you do with diazonium salts? Well, it turns out you can attack it with any group that can be considered nucleophilic, okay? So one of the things we can also do is to use it as a electrophile. So it has a partially positive charge on the end of it. So you can actually react benzene with the diazonium salt to generate an Azo compound. So an Azo compound is something that has a nitrogen, bonded to a carbon, double bonded to a nitrogen, and then bonded to another carbon. Okay, so because of the hybridization, these tend to be very conjugated systems, and they tend to be used in a lot of commercial dyes and colors and pigments. So instead of taking a nucleophile and displacing our nitrogen off the group, we're going to use it as the electrophile to attach to the benzene ring. And when we do that, we see that the group we're attacking directs where it attaches by its orthopara direction. So for example, in the case of phenol, we know that's an orthopara director, and therefore we can get attachment of that diazonium salt para to that hydroxy compound, and we generate what we call this phenyl azophenol compound, which is a deep bright orange. Okay, now by taking that OH off and putting something else there, we change the electronics of the system a little bit, and we can change the color. So in this case, if we use that same diazonium salt, and instead of using phenol, we use the dimethyl aniline, using very similar conditions right here. Just takes a little bit of base, and it will act as our electrophile and generate this compound here, which actually has a deep canary yellow color. Very deep canary yellow color. And the change in color has everything to do with just whatever here. So you can get these azo dyes everywhere from purple to red and everywhere in between just by changing that group. Okay. So that's another useful part of these diazonium salts. We don't just have to substitute them, we can actually use them as electrophiles. Okay, so we said before that lone pair of nitrogen acts as a nucleophile, which makes it very hard to stop it from reacting once you have a substitution. So for example, in a standard nucleophilic aromatic, in a standard SN2 type reaction, nucleophilic substitution reaction, once you get the one group added on, once it reforms its neutral species, it can still act as a nucleophile. However, by using, instead of the amine as a nucleophile in an SN2 type reaction, we can use it in an SAC2 or an acyl substitution reaction. Remember, in an acyl substitution reaction, we displace the weaker base, and in this case, it's the chloride, and generate mono substitution on there. Okay, just like when we formed all those amides, that acyl substitution stops at the amide functionality and generates a salt with the other equivalent of our system. Okay, so this is exactly like in our carboxylic acids chapter. So that is synthetically useful for us because we'll know we get that stopping at that first substitution in the acylation, where we don't do that in our SN2 type reactions. Okay, so now that we have these amines, there's a couple other things we can do with them. Okay, so the one thing we can use is we can use it as a leaving group and form an alkene from it by doing what we call the Hoffmann elimination. Okay, so in the Hoffmann elimination, we actually have an amine, and if we tried to take that amine off, it would be a bad leaving group because it had a nitrogen with an anion on it, and that's a very strong base. So that makes it a very bad leaving group. So in the Hoffmann elimination, we're actually tricking it to becoming a good leaving group before we do the conversion. So in the Hoffmann elimination, the first thing we do is we alkylate that amine, and we keep alkylating that amine until it forms a quaternary ammonium salt. So the first step here is we have our amine, and we just keep hitting with an alkyl halide. The first time it'll make the monomethyl, then the dimethyl, and then the trimethyl ammonium salt. Once it forms the trimethyl ammonium salt, now if we displaced it, if it left, it would leave as a neutral tertiary amine. That makes it a good leaving group, okay? So our next reagent here is our silver oxide. And in the case of our silver oxide, it's going to generate a salt with our ammonium compound here. And we get hydroxide out of it, which is a good base. Okay, so we're going to get our attack by our base, at our beta carbon. These electrons are going to kick in, kicking out our neutral amine species, and therefore we've generated a double bond, carbon-carbon double bond, and we have neutral leaving groups. We have both water as a neutral leaving group because it's deprotonating the beta carbon, and the amine, the tertiary amine leaving as a neutral leaving group. Okay, so that's how we are using the amine to help us generate a good leaving group. Now, so we had a primary amine, we kept hitting it with an alkyl halide until we got elimination by our system. Notice we used methyl iodide. The benefit of using methyl iodide is that make sure that there are no other beta carbons on that nitrogen. So the one that has the beta carbon on it, the longest chain here is the one that's going to have the alkyl group on it. And we're using the methane here so that there's no beta hydrogens to eliminate here. So we always get elimination at the longest chain. Okay, so we have elimination at that longest chain. Okay, so that also gives us selectivity. Okay, so let me show you. So we have regioselectivity in the Hoffmann elimination. Most E2 reactions, we have to have that beta hydrogen being counter to it. And so we end up with what we have elimination to form the more substituted double bond, or Zaitsev's rule. Okay, because it can wait and move around and form that more thermodynamically stable deprotonation spot, we always get that more substituted double bond. However, in the Hoffmann elimination, because we're generating this big bulky amine, we actually are forcing it to be opposite of the normal Zaitsev's rule, or we call it anti-Zaitsev's. So you end up with the primary product being the least substituted alkene. Okay. So just elimination of an alkyl halide using base, we always get the more substituted amine. In the case of the Hoffmann elimination, we actually get the less substituted amine. Okay. So the next reaction that helps us do this kind of selectivity of our leaving group, taking our nitrogen and making it leave, is a thing called the Cope elimination. Okay. In the Cope elimination, we're doing the same thing we did in the Hoffmann elimination. We're making the nitrogen a better leaving group. Okay. In this case, we take our amine, our tertiary amine in particular, and we oxidize it using hydrogen peroxide or peroxy acid, like in this case, we're using metachloroperbenzoic acid. That's what this is, MCPBA. What we're doing is we're creating an N-oxide. When you make an N-oxide, you're generating a positive charge on nitrogen. When you generate that positive charge on nitrogen, when it eliminates, it leaves as a neutral species, and therefore you end up getting it becomes a very good leaving group. Okay, so in this case right here, we would take a alkyl halide, and it works best if you have a dimethyl tertiary amine, because you want to make sure where that beta hydrogen is leaving. These methyl groups don't have beta hydrogens, only the other chain will have a beta hydrogen. And therefore, we react it with peroxide and then heat it up, and it eliminates this hydroxylamine plus our alkene. Okay. And because we've selected exactly where that nitrogen is going to leave from, we do not have a carbocation intermediate. We do not get rearrangement. Therefore, the double bond is always going to be formed where that nitrogen was and the most readily available beta hydrogen. So we can end up with things like having our double bond outside the ring, Whereas if we try to do a dehydration with an alcohol, we would always end up with the more substituted one where the double bond would be in the ring. Okay. So in both the Cope elimination and the Hoffmann elimination, we've changed nitrogen into a positively charged species to make it a better leaving group so it leaves as a neutral species when it takes its electrons with it. Okay, so those are all the reactions we have for the amines. Again, we're looking at selectivity here, okay? We can make primary amines, we can add a carbon, we can take a carbon away, we can keep the same number of carbons, okay? We can get anti-Zaitsev rule eliminations by making nitrogen into a good leaving group. We can add things to benzene rings by making nitrogen a good leaving group, by making it the diazonium salt. And therefore we can get two reactive products we can't get in other ways. So that's a great thing about using amines as an intermediate, because we can get to that selectivity. Okay. Any questions on the reactions? Okay, I have 10 minutes, and what I want to do is I want to walk through some of the spectroscopy related to amines. We hit a little bit on this when we talked about other systems, but I wanted to hit on it here again. So with spectroscopy, one of the cool things in mass spectroscopy, which is way back in chapter 9, is that nitrogen has an odd molecular weight, okay? Which means that you can always tell when you have nitrogen or an odd number of nitrogens in your compound because your parent ion peak will have an odd number, okay? So if you have 1, 3, 5, 7 nitrogen in the compound, you're gonna have an odd number. However, it doesn't work if you have an even number because 2 odd numbers add up to an even number. So we have an interesting way of identifying if you have an odd number of nitrogens in a compound just by looking at the mass of the parent ion peak. Okay, I talked about this when we talked about IR. Amines and amides, if they have 2 hydrogens on them, so if they're primary amines or amides, you'll have 2 peaks in that high end range above 3000. Primary amines and amides only have 1 hydrogen that absorb in that area, and tertiary amines and amides have no hydrogens and therefore do not absorb above 3000. In NMR, just like when we had alcohols, that electron-rich species shifts the peak up from where you'd expect it to be bonded to a carbon-hydrogen bond, typically in the 3 to 5 range. However, that varies with the amount of hydrogen bond you have. In fact, the more hydrogen bonding you have, the broader the peak gets and the more it shifts around. Just like with alcohols, the hydrogen that's 2 bonds over from it is shifted higher than with a regular compound. And in carbon NMR, it's the same thing. It's shifted about to the 30 to 50 ppm range, up from about 10 to 20. Okay, like in the alcohol species, it does exchange when you add acid to it. And like alcohols, you do not split through a nitrogen. You don't split through an oxygen, you don't split through a nitrogen. So what that means is it actually helps clean up your spectrum. So for example, in the case of this diisopropylamine, we see the splitting pattern. We'd see whether if there were no hydrogens on this atom at all. So this nitrogen here, because it can hydrogen bond, it's actually this little tiny peak right here. It's really broad. And it's not split by any of the hydrogen. Okay. Our B hydrogens, which are the ones here in the middle, are only split by the 6 hydrogens that are non-equivalent to it in adjacent carbons 3 bonds away. Therefore, we get our septet. And these are only split by our B, so that's getting a doublet here. Again, you do not split through a nitrogen or an oxygen in proton NMR. I think that might be my last slide, actually. Yes. All right. So that is all of amines that we're going to do. The reactions are the most important part of this, and naming primary, secondary, and tertiary means. Okay. Questions before we break for the day? We have about 4 minutes before our scheduled class time, so we have plenty of time for questions. I'm take a sip of water while you formulate a question. Excuse me. So you'll be happy to know I finally got into my allergist, so hopefully he can help cure my cough and get me this. In fact, I have it right after this class today. So, all right, I'm going to go ahead and stop recording.